potential energy stored in dipole. Potential energy stored in a dipole. So we have to take here, this is the electric field and this electric field is uniform in nature. This is the uniform electric field E, and a dipole which is placed in this electric field is like that. This is our dipole, this is minus Q and this is plus Q. This is the bond length of the dipole, and this distance is to be always taken to be L. Here we see that if this dipole is rotated at an angle of theta, then the energy will be stored in this dipole. It means if dipole is rotated, this is minus Q and this is plus Q. If that dipole is rotated at an angle of theta, the torque acting on the dipole, in the previous lecture we have to discuss the torque acting is PE sin theta. This is the torque acting on the dipole. Torque acting on dipole. This is the torque acting on the dipole. Tau is equal to PE sin theta. And if a small differential work done is defined from here, because this system is to be rotational system, and force is replaced by the torque, and this linear displacement is replaced by the angular displacement, because the work done formula for the linear quantities is F dx, and here this is the work for torsional, and force is the replaced by torque, and linear displacement is replaced by the torque, angular displacement. So here the formula for the work done is equal to tau into d theta. Hence, from doing this, if this dipole is rotated at an angle of theta, so some amount of work is to be done by the external agent. So hence we say that the total amount of work will be calculated as torque into d theta. What is the value of the torque? The torque value is PE sin theta, and this is the d theta. Now we have to interested to know all of the work which is the doing in this process is known as all the work which is stored in the form of potential energy, and this is the total work. So we have to integrate total work. So dW is equal to integration PE sin theta. What place the value of this 1 here, the value of place the theta 1, and this is our, because the dipole is rotated from the position of theta 1 to the position of theta 1. The net amount of work will be W is equal to P here constant, so we have to take out this value from the integration, and integration sin theta d theta. What is the value of integration sin theta d theta? Is minus cos theta. This is PE minus cos theta, or limit is going from theta 1 to theta 2, because the dipole is rotated at the position of theta 1 to the position of theta 2. So the best result is coming here. PE minus sign is taken from here. Here in the bracket of cos theta is undertaken under here. So we will place the value of upper limit cos theta 2 minus lower limit cos theta 1. Here the theta is placed first as the upper limit and second as the lower limit. So first is the using the upper limit, minus sign is taken from brackets. So cos theta 2 minus cos theta 1. And the net value of the work done is minus PE cos theta 2 minus cos theta 1. Minus sign will be, we have to multiply here. So here we see that PE is equal to cos theta 1 minus cos theta. This is the formula we have to remember for doing the work. So here we see that this work is stored in the form of potential energy, because this is a conservative force field. Hence we say that all the work this is stored in the dipole is in the form of potential energy, because electric field is a conservative force. Hence all work is stored in form of potential energy, and we are using the sign of the potential energy U is equal to Pe cos theta 1 minus cos theta 2. This is the formula, so we have to remember it. Here the theta 1 is the general locations where the dipole should be rotated, and theta 2 is the final location at where this dipole is to be rotated. From here we see that if the dipole is suppose rotated here, and this is the angle of theta 1, and this is the final location, the dipole is rotated, and this is the angle of theta 2. This is the position of theta 1 and theta 2. In general locations, the theta 1 is the in stable conditions, where theta 1 is equal to 0, because generally the dipole is rotated at the angle theta 0 degree, because this is the stable condition of the dipole. This is the stable condition of dipole. So now we here the place the value of the for the simple calculations here we have to introduce that U is equal to Pe. If the dipole is rotated from the stable condition, then cos theta 1 is 0 degree minus cos rotated at the general angle theta 2 is equal to any theta. So here we see that Pe cos 0 is 1 minus cos theta. This is the potential energy which is stored in the dipole when this is in stable conditions.